Hello, everyone. Have you ever stopped to think about what keeps your feet on the ground, or how the moon stays up there in the night sky, just circling us? Well, the answer to both these questions is a powerful, invisible force called gravitation. And today, we're going to understand this very important force that shapes our whole universe. It all begins with a very, very simple question. A question that I'm sure all of us have asked at some point. When you drop a pen, or a book, or a ball, why does it always fall down? Why not up or to the side? This simple, everyday observation, you see, is the first step to understanding one of the most fundamental forces in nature. And the story of how we figured this out is quite famous. Just imagine the brilliant scientist, Sir Isaac Newton, sitting under an apple tree. And suddenly an apple falls down. Now, for most of us, that's nothing special. But for Newton, that falling apple started a chain of thought that would change science forever. Newton looked at that fallen apple, and then he looked up at the moon. And he asked a truly amazing question. He thought, is the force that's pulling this apple to the ground the very same force that's pulling on the moon, keeping it in the sky? Before Newton, you see, people believed that the laws on Earth and the laws in the heavens were completely different. So connecting a simple apple to the giant moon, well, that was a revolutionary idea. And this one powerful question led Newton to formulate one of the most important laws in all of physics. This is the heart of our discussion today, the universal law of gravity. Now listen carefully. Newton's law says that every single object in the universe attracts every other object. That's right. You are gravitationally pulling on your chair, the Earth is pulling on the sun, and a star that is millions of kilometers away is pulling on you. And this force of attraction depends on two main things: how much stuff is in the objects, that's their mass, and how far apart they are. Let's break this down. The first part is about mass. It's actually quite simple. The more mass an object has, the stronger its gravitational pull. So a huge planet like Jupiter has a much stronger gravitational pull than a small moon. It's as simple as that. More mass means more gravity. Now, the second part is about distance, and this one is a little bit tricky, so pay attention. The force gets weaker as things move apart, but it weakens very, very quickly. We call this the inverse square law. Imagine you're sitting near a small campfire. If you move back one step, you feel a little less heat. But if you double your distance from the fire, you don't feel half the heat. You feel 1/4 of the heat. Gravity works exactly like that. If you double the distance between two objects, the force of gravity between them becomes 4 times weaker. Now, to turn this idea into a proper mathematical formula that we can use for calculations, scientists use a special number. We call it the universal gravitational constant, or simply big G. And the amazing thing about G is that it is the same everywhere in the universe. On Earth, on Mars, in another galaxy, this number is always the same. And that is why we call the law universal. So that's the theory. But what does this look like in the real world? Let's look at some fantastic examples of gravity in action all around us. Let's go back to the moon. The moon is moving very fast, so why doesn't it just fly away in a straight line off into space? The answer is Earth's gravity. Our planet is constantly pulling the moon towards its center. This pull is called a centripetal force, which is a fancy way of saying center seeking. It's just like when you tie a stone to a string and swing it around your head. The string is constantly pulling the stone inwards, forcing it to move in a circle. For our moon, gravity is that invisible string. Okay, here is a very interesting question for you all to think about. We know that the Earth pulls the apple down, but remember what the law says? Every object attracts every other object. So, does that mean the apple is also pulling the Earth up towards it? What do you think? And the answer is, surprisingly, yes. The force is the same. The apple pulls on the Earth with the exact same force that the Earth pulls on the apple. So why on earth don't we see the Earth moving? Well, think about it like this. If you push a small toy car, it will move very easily, right? But what if you push a huge bus with the exact same force? Will the bus move? Not at all, because the bus is so massive. In this case, the Earth is like the bus, and the apple is like you pushing it. The pull is there, but because the Earth's mass is so enormous, its movement is so tiny that we can't even measure it. What was truly incredible about Newton's law was just how many different things it explained with one single idea. Suddenly, we understood why we are stuck to the ground, how the moon orbits the Earth, why all the planets go around the sun, and even what causes the tides in our oceans. It was one simple rule that explained the whole cosmos.
Now, understanding gravity helps us clear up something that many students find confusing: the difference between mass and weight. In everyday language, we use them to mean the same thing, but in physics, they are very, very different.
First, to understand weight, we need to quickly understand the idea of free fall. Whenever an object is falling only because of gravity, with no other force acting on it, it speeds up, it accelerates. And this special acceleration has a special name. We call it the acceleration due to gravity, and we use the symbol small g for it.
So let's compare them now. Your mass is the amount of matter, the amount of stuff that you are made of, and this is constant. Your mass is the same whether you are on Earth, on the moon, or floating in outer space. Your weight, on the other hand, is the force of gravity pulling on your mass. And since the pull of gravity is different in different places, your weight can change. Weight is a force, and so it is measured in newtons, not in kilograms.
This becomes very clear if we imagine going to the moon. The moon is much, much smaller than the Earth, so its gravitational pull is much weaker. In fact, the gravity on the moon is only about 1/6 as strong as it is here on Earth. So, if you went to the moon, your mass, the amount of stuff in your body, would stay exactly the same, but your weight would be only 1/6 of what it is on Earth. So, the most important thing to remember is this: the mass of an object is always the same, no matter where it is, but its weight depends on its location, because gravity is different at different locations. Mass is constant, weight changes. So let's just step back for a moment and think about what we've learned. We have been exploring one of the 4 fundamental forces of nature, the invisible glue that holds our entire universe together. It's really quite amazing when you think about it, isn't it? We started with a simple falling apple and ended up with a beautiful, elegant law that describes the motion of entire galaxies. That is the real power and beauty of science, finding the simple rules that govern our huge, complex universe. Gravity truly is the force that connects us all. And that leaves us with one final big question to think about. If gravity is always pulling everything together, all the stars, all the planets, all the galaxies, then why hasn't the entire universe just collapsed into one single giant point? That's a wonderful question to think about. Thank you for joining me today.